Okay, so we are live again, another Friday. Thank you everyone for tuning in. Let me just do, I know Soham can hear me. What about the rest? Can you all hear me and see the slides? Okay. Okay, great. Fantastic. Let me just maximize this. By the way, if the resolution is not okay for any of you, just let me know so I can maybe adjust it. But I haven't changed the default from the last session, so hopefully it's okay. Yeah, so today, this is the agenda. Just go through the normal pre-lecture comments, just to comment on some stuff about this thing is discharging. I was about to run out of batteries. So we'll start with the pre-lecture comment, the usual stuff, then go through some basic kind of recap of the important stuff that we covered last time. And then finally start through the general definition of the n-by-n matrices. And then we'll then switch focus to square matrices, in particular square matrices as operators, because this is what we want. They are the ones that will provide us the operators that we are interested in quantum mechanics or in quantum computing. And then we'll go through some basic operations, and so on. And then finally, we'll do some comments on the study materials. That's it really for today. Hopefully it will be very short. And then next week, we will carry on from where we are left today. Oh, so first of all, congratulations to all of you who made it this far, really. So you can see, it's been a long journey from the, the moment we started, like back in September, I think. And you can see everything is green. Most of the things now are green, but we are halfway through. So we are here. For those of you just joining us today, or those who are watching us on YouTube. So this is the first, this part here has two, this section has two parts. This is part one. And this is essentially, this section is really to prep you for this other section, and hopefully also prepare you for these other two sections, really. So let's say it's a kind of a lightweight, as opposed to hammering you everything here, we will just introduce some concept that hopefully will save us time, so we can dive deeper into these other, into the stuff in this section. So yeah, so just another way to view this section is like, 101 of this section, really. 101 plus, because we will also touch some stuff that are relevant to the quantum stuff, okay? But just lightweight touch. And another thing I want to comment on this, since we are in the foundation module, I just noticed, I realized we are in November, December is coming fast. So given the situation, at least in my case, I have plenty of time on hand, because we are on lockdown here and so on. I will be flexible in order for us to make it possible for us to box this module before Christmas, to either in the towards the end of this month, or maybe probably early December, we can have like double sessions, so we can cover the stuff before Christmas. That way, everyone goes on Christmas very happy that you completed the foundation module. And in that respect, in that regard, I don't really have any preference for the days. I guess it's something that I will check with you. I will send a survey to see which days of the week is best for most of you. I don't even mind the week, like to do weekends also, because my Christmas is spoiled anyway because of lockdown, so it's not a problem. So just to let you know, I will be sending a survey, maybe not this week, the week after, to see if you guys, which day, if you are, first of all, you are okay with doing double sessions, so we can move fast and box this foundation module. Okay, So let me check. Okay, I would like to complete this module before the end of the year. Yes, so hopefully it will be the biggest Christmas present for you guys. So, so it seems there is definitely interest. I can sense this thing. Okay. So let's go through. So the recap, the most important thing from last session is this theorem that says, two vector spaces are isomorphic only if their dimensions are the same. And we also saw that, this is another, a more interesting way or elegant way of saying it is to say these statements are equivalent. So if you prove one thing, the other one follows. Another thing we saw was that any finite dimensional vector space is essentially isomorphic to Cn. Okay, so that means, because in this section we are focused on finite dimensional complex vector spaces, in practice we can start just working with the Cn. So that's very very important, which means we can use the matrices, the n by n matrices as operators. So even if we have we start working on an abstract vector space, and because the vector space is isomorphic to Cn, maybe we can do theory in the abstract vector space, but then do the computation on Cn, because we know pretty well how to deal with the matrices. There are a lot of software that can do that. Okay. Another thing we saw is this thing of invertibility of linear operators. Obviously, this is we will touch invertibility today, but in the matrix context. But obviously, because matrices are linear operators, then therefore, anything we say about linear operators also applies to the matrices that we will be working on with today, starting today. So I hope you managed to prove this. You didn't have any issues. It's not a problem if you did, because I didn't get any ping on the chat, so I assume this was okay. Or maybe some of you might take a little bit of time to realize this, but that's fine. Another thing we saw is that this is very important. We will see this also again, but in the matrix in a more concrete sense, is that the product of two invertible operators is also invertible. So that means the set of all invertible operators is closed under multiplication. Okay, and we saw these examples, and most of you guys already seen these. These are the most of you coming from quantum computing. These are like the gates. They are unitary. What unitary means, we will get to that, but they are invertible anyway. So another thing we went through is the concept. This is the abstract concept of eigenvalue and eigenvectors, and the reason we did that is so that to prepare you that to put in your mind that these, even though in most of the cases, like when you deal with the basic intro to quantum mechanics, or even in quantum computing, you mostly get exposed to these concepts through matrices. But the reason I mentioned them in the abstract sense is that these concepts are very abstract. They might have nothing to do with the matrices, which is the case when you will see some of you decide to move on to the next module, which will deal with functional analysis, where you will come across very strange operators that have nothing to do with the matrices. Okay. The quantum matrix operator section on the foundation module will be all about computing this. How do you do this and these things? And today already you'll start to see where things are heading and these things. Okay. So another thing we saw is that giving an operator T with distinct set of eigenvalues, lambda 1, lambda 2 to lambda n, with the corresponding eigenvectors, then the eigenvectors are linearly independent. This will become more relevant, interesting once we get to Hilbert spaces section, and once we start talking about orthonormal bases and these things. But it's very interesting. And then I hope you you could kind of get to this answer, whether if the dimension of n happens to be the sequence happens to be the same number of the sequence, the index n here, whether these vectors form a basis. Another thing we went through is this is more of a kind of awareness, especially if you go on to read books written by physicists, is often that they write this, they write lambda 1, lambda 2, blah, 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 just to denote the eigenvectors. So instead of writing this, they would write this, which is, if you don't know, you become very, very confusing. So it's very important to notice this, because there are a lot of standard textbooks in quantum mechanics that you will see physicists write this. And if you don't know, it becomes very, very confusing. What do they mean with this? Putting a complex number in here and then call it a vector. So that's where we are. Let's now go to the new stuff. I assume there was no questions. Let me just go back, and everyone is listening and no issues with the sound, so we can carry on. Okay, so this will be really, I know some of you, I apologize, most of you, I think, I can safely say, looking at the audience, all of you, you already know all this, but, bear in mind, there are other people who will be watching this on YouTube. So, we're going to start with the kindergarten stuff. So apologies, and apologies in advance if there is any typo somewhere, because, I only had 1 hour to prep the slide stuff. So, yeah. So anyway, given M and N, we define N by M by N matrix over C. So a matrix with the entries in C. So the entries here are all like complex numbers like this. And often you see the abbreviations written like this. So this is like very easy. The index I indicates the row, the J indicates the column. Okay. So for example, this entry here is this one. So it indicates the first row and the first column. Okay. Another thing that worth mentioning is these elements here. These are very interesting elements. In fact, today we will come across them. They are called diagonals. So these are the diagonal elements of this of a matrix. Okay, and often it's written like diag of A or diag of something like this, depending on the author. And A is called a square matrix if M equals N. This is exactly the case that we are interested in. So we are interested in using in N by N matrices because they are the ones that will give us the operators from Cn to Cn. Okay, and this is already in the group section and the ring section. You already being exposed to this. Maybe we work with a more concrete, like a toy example. In this case, with M2 of C. But in general, today we will start working with the general setup of this. So M2 of Mn of C is the set of all N by N matrices. It's to be understood like that. We have seen that given an element of Mn of C and given a ket vector, actually I shouldn't call it ket vector. Let's just call it vector for now. Once we get to Hilbert space, we call it ket. Yeah, or let's just call it ket vector anyway. It doesn't matter because we're already using the ket notation. So yeah, so given a matrix in Mn of C and a ket vector in Cn, A can act. We have seen this I believe in the previous sections, that it can act as an operator as this. So this is essentially the matrix multiplication. So it's like this matrix multiplying by the column. This is N by N matrix multiplied by column. Really, this is it. This is the thing. So you take the first entry, you multiply it with the first column, you add it with the the second entry on the cat multiplied with the second column, blah, 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 okay? The good thing is nowadays nobody really does this manually, okay? So even if you have issues with doing this and these things, you know, you don't have to do this manually, though it's very useful to know how to do it manually. Okay, so that means because A is a linear operator, obviously all the stuff that we mentioned about operators also applies to A, right? Things like eigenvectors, eigenvalues, blah, blah, blah. And one thing that I didn't do, I forgot to include on this slide is to show you that any abstract linear operators in CN, there is a corresponding. We can, you know, by fixing a basis, we can generate a n by n matrix. But I believe it's on the test book, so you know, you can look at the thing. How do you get from, you know, an abstract to a concrete matrix, a concrete representation of an abstract operator? Okay, it doesn't really matter actually in that sense, because we can just jump and start working with the matrices anyway. So, but if you have any issues, you know, just ping me on the thing, on the GitHub. Okay. Let me check. Okay, so addition again, you know, this is like kindergarten, you know, I feel like I'm offending you guys. You know, it's the same thing. So you add individual entries, you know. I'm pretty sure if there is a typo here, some of you will let me know, and I apologize in advance. And, you know, the key to note is, you know, and this is also very obvious for all of you on the audience, is that, you know, the addition is commutative, right? A plus B is the same as B plus A, and it's also associative, right? You have all this. So, and by the way, since we are in addition, you can also define, you know, subtraction the same way, you know, by subtracting the individual elements. Obviously, you do the operation in the thing in C. So this is like kindergarten stuff that I will just jump straight, so I don't want to offend you guys. The same with this. Scalar multiplication is, you know, essentially just multiply with you know, multiply the alpha with, you know, the individual entries of the matrix. Okay, kindergarten stuff also. And in fact, from the section of vector spaces, I'm pretty sure most of you already seen that this is a vector space indeed over C. A very interesting thing. This is the most interesting part of this. This is one of those quantum hints. I want to go into discussion about this. I might add one extra session after we go through the Hilbert spaces to this concept of C-star algebra. This is very important because in the so-called, you know, the density matrix formalism of quantum mechanics, you know, where the state is not, as, you know, in the standard textbook, they say to you like, a state is a vector in a Hilbert space, blah, blah. That's a pure state. There's also something called mixed state that we will touch on when we discuss the axioms of quantum mechanics. Essentially, behind scenes, you have like, you know, the mathematical toolkits behind it is really C-star algebra, really. So we might touch this once we go through the Hilbert space, the standard Hilbert space formalism that the textbooks talk about. We might touch this, have like a session as an optional session for those who want to attend. Okay. Okay, so multiplication. So I hope I got this right. I didn't want to give the formal, you know, multiplication, the more formal thing, which is I find it when I was my students, very confusing. But hopefully this creates a kind of shortcut for you guys, you know, for especially for those watching on YouTube. And most importantly, you know, nowadays, you know, you don't really need to do like a manual, you know, manual computation of the product of matrices. But if you need to do, tend to notice is just here's the trick to do it. Okay, so you take the columns of this. So the resulting product matrix is a large matrix. Obviously, it will also be n by n, and and you do it like this. So you take the column of the matrix B, and then you view it as a vector, okay? And then you apply the other matrix to it, pretty much in the same fashion as this, what you've done here, okay? This is essentially the same thing. So that's what you do. Hopefully there is no typo somewhere. And then it's easy to see that in general, I hope this is also clear. I'm pretty sure all of you on the audience, because I know you already know this. The product is non-commutative in general. It's also distributive. So this essentially makes Mn of C. We already seen on the example with the rings, we saw M2 of C is a non-abelian ring. Well, Mn of C is also a non-abelian ring with identity. So look, notice the identity for this will be like everywhere else is 0, but the diagonal entries, they are all like ones, okay? So this is not a problem, piece on the cake. Okay, let me check the chat. Okay, so by the way, if you spot any errors or something, please let me know. Because as I said, the slides might be, I did them like in less than an hour or so. So invertible matrices, just like we've seen. So this is a more concrete, so the concrete notion of invertibility of an operator, really. So given a matrix, in Mn of C, it is invertible if there exists another matrix that we called A to the power of -1, so the inverse matrix, such that the product between them yields the identity matrix that we just saw before, okay? And now we have this also, that if A and B are invertible, then their product is also invertible. And also, this is true. The inverse of the product is the same as the inverse of B times the inverse of A. So I will leave this as a homework for you guys to prove this. Just by going through the rules of the multiplication, you will be able to prove these identities. Okay. And so this means that the product is obviously closed in the thing under the multiplication. So essentially this means the set of all invertible matrices in Mn of C that we write like this is a group. We have seen this also in the group section, okay? So this is a group. This is in the matrix group section. We will be working with this. More interestingly, the subgroups of, because this is too big, we will be looking at the subgroups of this, like the general linear group and the special linear group and so on, okay? So another thing to note is that an alternative notation, I like using this. Somehow I don't like using this, but a lot of authors use this notation. So they mean the same thing. So if you see this, it means this. So this is called the general linear group of invertible matrices. Okay. Check the chat. It's been a while. So should be just the okay. So Cj is actually should just be another vector of size. Okay, I cannot see the other previous question, so I cannot put the question in the contest. Maybe I will come back to this just for the interest of time. There's another one. Okay, so this one, the way you're describing, okay, let me go back to the slide. Okay. So you mean here. So this is just, so imagine this is like, this is the matrix here, this one acting on this. Imagine this is the psi. this is essentially this this matrix multiplying on the column this thing here. So another way to say this is like this is this. Okay, this is this essentially. The only thing, instead of this being this psi, it's the columns of this other matrix. Does that make sense? Okay, let me go back again to the slide. Did I lose everyone? Let me go back again. So we have A, okay, and psi is a column. This is a column vector, right? Okay, and the column vector, this vector multiplied by acting on this is this, right? So you apply the same principles, to this. It's essentially a very large matrix, but inside you are actually doing the thing. So you are taking you are multiplying, you are acting. So this matrix A is acting on the columns of this, the B, if that makes sense. Yeah, there are different ways of the thing. This is different. This is the hack that I could find looking at the formal definition, obviously. But so yeah, I hope I got it right. Right? Huh? Maybe you can do some thing and find a counter example. Okay, but it should work. I thought this is the simplest way of showing you a concrete way of computing the product. So it's just you open you obviously it's a large matrix. It's the same size, by the way, and you just take the columns of the second matrix B, and then you pretend obviously it's a column matrix, and then you just act. The result of this should be another column matrix, so that will be the first column of this the product matrix. Okay, and then you do the same for the second column. Okay, and then you go on until the last column. So the result, you should have an n by n matrix also in the thing. Okay. So let me go back. Either way, you don't really do the you don't have to worry about doing the manual computation. Oops, I'm going too far. This is not what I want. Mostly, you have software that does this, for you. You don't have to do compute. The key to note is that the some of the properties of the product, some of the stuff, and this is the thing. Like, most of times you do like abstract. You work on these things not in the concrete fashion, but in the abstract sense. So, of course, it's very important to know what's happening behind scenes. But when it comes to like maybe toy examples like small matrices, it's very easy to work with. But suddenly you become like with the when you are dealing with 1,000 times 1,000 matrices, you know what I mean? The size then is like it becomes impractical, right? You can't do that in manual. I mean, you can try to do it. Good luck with the thing. I don't have patience for that, so I don't think anyone does. Okay. So where were we? So yeah, in the invertibility. So we have seen this, and we have seen this is the notation is the same as this. Let's go to the next important thing, which is the diagonal matrices. There are a lot of things that today we'll just cover some basic stuff. Next week we will introduce more concepts. For example, we'll get into the concept of Hermitian matrices and these things. Okay. A diagonal matrix. So an element of Mn of C is diagonal if every non-diagonal element, every non-diagonal entry of the matrix is 0. Okay, so except these entries, so everywhere else is 0. Okay, so this means that, you know, obviously Aj, this is in a formal way, the entry Aj equals 0 if it's getting too late here. Aij equals 0 if the index I is different than j. Okay, so that essentially means this, that everywhere on the matrix except the diagonal entries are all 0. Now, this obviously, by definition, in principle, there could be, in the diagonal here, somewhere there could be an entry that's also 0, obviously, right? Like in this case here, you know, this is a diagonal matrix. You know, it has a 0 there, but so what? There's there's another. I mean, it satisfied the condition. You know, all these other non-diagonal elements are all 0, so it's a diagonal. It's a diagonal matrix. Obviously, we don't want the case. The case that we are interested in is where not all of these elements are 0. If they are all 0, then it's like the 0 matrix, right? That's boring matrix, right? We don't want anything with that. Okay, and more interestingly, there will be some matrices we'll see in a minute, in the second, that are very interesting. The ones that have the diagonals that are all non-zero. So all these non-zero elements of these elements are non-zero. Those are very interesting matrices that we're going to touch. We'll see them in a minute. Okay, so this matrix is also diagonal, right? This is one of the, some of you will already know, this is one of the quantum gates, one of the Pauli matrices, right? Okay. This is a home challenge for you. So if A and B are diagonal matrices, then the product of the two matrices is also diagonal. And interestingly, they commute. So diagonal matrices commute, okay? So I challenge you as a homework to go and try prove this, obviously using the rules of multiplication. You don't necessarily have to use the way the rules, the way I laid out to you, the multiplication. If you find another way of the thing, you can use that also. You know, it's just my claim is that you will be able to prove that the product of two diagonal matrices is also diagonal, and that two diagonal matrices commute. Okay. See. Okay. Okay. So, and now the question is the invertibility condition for a diagonal matrix. This is very interesting. We will see this later once we reach to Hermitian stuff section, and more concretely once we start talking about the actual, quantum stuff. So anyway, given a diagonal matrix D, let's call it D because it stands for diagonal, with the entries lambda 1, lambda 2, blah, 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 to lambda n, the following statements are true. That's the claim, that D is invertible if only if the lambda i's are non-zero. Okay, so that means all the diagonal elements are non-zero. So that's the claim. So if there is something here, if there is a 0 here, then this means that the claim is that this is not invertible. Okay, so hopefully you can prove this. Hopefully you cannot prove the other way around. And the second thing is that the inverse is given like this. So this is the inverse. Okay. Let me check. So this is homework. I mean, home challenge for you, that a diagonal matrix is invertible only if the diagonal elements are non-zero. Okay, and the inverse of its inverse is also given is on this form. Okay, that's it really. I said the session will be very short today because I wanted to take it very easy, and also because I was late to prepare the slides, so I couldn't add some of the stuff that I wanted to add for this session, but not a problem. We'll add that next week. So for this section, section 3C, matrices, pages 70 to 78, you will see his, I think he might have a different definition of a different way of presenting the product. So, and actually I have another book that I wanted to share, but because it's free, I'm not sure about the licensing thing. That's why I didn't want to share until I double check. So maybe next week we will start using another reference book for you guys as self-study material. I wasn't sure about the one that I have with me, whether it's possible to share it. I have to read the license to see, because we don't want to be a situation where we upload it to GitHub and then we get a notice that we should have. We shouldn't share it. So that's it really. Let me check the chat. So Amir is asking, any significance to the difference? Versus, I cannot see, this is the thing, there is no, this chat doesn't support Gitter, and sometimes when you write something, I cannot, I don't, because it doesn't format in the mathematical typeset, so it's like, I don't see what you are writing. If I go back to slide, okay. Which slide? I assume is the inverse. Yes. What about it? So.
Yeah, I think the question is, what's the difference between using the brackets and the parentheses for the matrix?
Okay. There's no difference. There's no difference. I forgot. This is just on the LaTeX thing because there's no difference. There's no difference. It's just this is on LaTeX. This is I'm using P. This is the P matrix thing. I'm using it. This the P bracket. This is a B. So it doesn't matter. It's just a notation thing. I will correct this on the slide. Thanks for noticing. It's just yeah. Yeah. I should be. That's right. I didn't notice actually. I should. It's very important to stick with the convention. And I know I like using the thing. But in the textbooks or something you might find this. So, but it's a thing. I will correct the LaTeX the thing. The thing. It meant to be like this. So there's no difference. Okay. So sorry for that. Was there any other question that I couldn't catch before? So there was something that I couldn't catch because I think it was like more of a thread between.
No, I think you actually answered that question. It was about the matrix multiplication, and you did talk about that.
Okay. Yeah, I mean, this is it's like nobody does really manual matrix multiplication really. So, but it's good to know. I find it the way it's formally presented it might be very confusing for a newbie. That's why this is hopefully the hack. Hopefully it works. It's much more easier to see it in the concrete way. that way, then others have other tricks to say the same thing. At the end of the day, it's the same thing, really. But in general, really, you use software to do it. The key is just for you to know the properties of the matrices, like it's non-commutative and these things, But obviously, for sometimes you want to do like paper or manual calculation, especially if you are working with toy models like 2x2 matrices and these things. Okay. Maybe let me just go back to the things we have a little bit in hand. In here. So next week we will we'll have like some extra stuff, some of the stuff that I didn't cover here, just to give you a bit of a lightweight, put your head in the right frame so we can get here. This is a very interesting section where we're going to talk about unitary. So you will know here what a unitary matrix is and these things. Okay, before we even touch a Hilbert space. This is one of the things in a lot of, from my point of view, a lot of these introduction courses on, especially in quantum computing, I've seen all these introductory courses, where they skim through the maths, they go in, oh, a unitary matrix is this, blah, 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 or a Hilbert space is this, blah, blah, blah. We'll do things, at least I will try to do things in a clean way, okay? Because the purpose of this course is really, for those of you, hopefully, you will gain enough knowledge to be able to, understand a lot of the stuff, maybe a lot of stuff that you already knew, but in a much more cleaner mathematical fashion that will help you dig deeper. And maybe, who knows, you go and they create a new theories and these things, or, create new algorithms, So that's the purpose of this. That's why we are, we took all the thing by going through, step by step stuff. Is like a painful, but for those of you, especially the ones online now, I think, hopefully it's been very useful. Actually on that, I would like to check how many of you, I know maybe not many, most of you with already like, coming from advanced background. How many of you so far, have learned something that before this course didn't, or understood something that before the course they didn't? In other words, I'm just trying to fish. So far, has your mathematical knowledge improved a little bit? Okay. Well, that's good to know, because this is really one of the purposes that we decided to do this, or and hopefully as we go along, this is just like the intro in the advanced module, especially for those of you like I'm sure Sohams and maybe CJs and the others who are interested in physics. Okay, so yeah, Amir is saying you didn't know the difference between sets. Yeah, this is the thing. I find it very frustrating. That's why sometimes when I see these talks, when people like in quantum computing, people skim through stuff, they don't talk, about all these building blocks that make these other stuff that they talk about. They, mathematics is like, it's like, how do I say? It's like a domino. It's like the thing, it's like a piece of puzzle, everything is built on top of things, on top of each other, So if you don't know the stuff, you will struggle to you might be able to do like computations and these things, but to do theory or do other stuff, it requires a little bit of digging about the foundational stuff. Okay. My understanding could just jumped into vector space with no okay. This is why I I decided to start with with this, with sets, because they are like the building blocks of mainstream mathematics. There are other, there's something called category theory. This is something that maybe in the future, if we might offer a course. In fact, my colleague and I, we are thinking about offering something called this will be more for advanced stuff people. on geometric quantization. There's heavy deployment of category theories and these things in there. Yeah. So anyway, there are people working trying to build the foundation of mathematics on these objects called categories. But set theory is the standard. The standard way of building. The way mathematics, certainly the mathematics that you are interested in doing quantum mechanics, is really set theory. So by starting with set theory and then doing it, these steps until we get here, So I hope it was helpful, because a lot of the stuff that I hope obviously you realize that a lot of the concepts have nothing to do with the Hilbert spaces, So a lot of the concepts that you learn, kind of you already learn a lot of these stuff before we even got Hilbert spaces. I found this hopefully very very useful for you, because then once we get Hilbert spaces, you will feel far more comfortable. We can focus on the actual things that really matters, as opposed to the other stuff that we went through, because you already know them. So yeah, and another thing is quantum mechanics. The mathematical formalism is actually it's for those of you especially those of you studying physics, the Sohams and these things who want to who will probably go further. It's a very interesting. The mathematics of it is not just about Hilbert spaces. And there are other interesting mathematical structures in play behind scenes. Like Banach spaces. Which we will cover hopefully in the functional. We have to cover Banach spaces in the functional analysis section. And in fact, there are situations where it's not ordinary Hilbert spaces. It's something called rigged Hilbert spaces, like rigged elections, right? So so it's really very. I hope it will inspire you, like some of you studying physics, or maybe the other ones also interested in quantum computation, to go and hopefully having this foundational level stuff, to go and dive deeper into the advanced stuff, because it's really very interesting. Interesting stuff out there. By the way, will the next module start right after this one? Maybe not right. I might deserve a bit of break. Whether it's me, it depends. If it's me, not my colleague, then I need a few weeks break, just to, especially after the lockdown. But yeah, it will be after this one. Yeah, and it will be most like functional analysis, and we'll cover a bit of measure theory. Yeah, and hopefully then you will be able to know how to deal with the infinite dimensional Hilbert spaces. And hopefully by then, like if you are like studying physics, advanced like theoretical physics, and hopefully you interested in mathematical physics, you will learn enough mathematical stuff to be able to to play with things like quantum field theory and so on. Okay. Yeah, maybe it's looking more like maybe February. So if it's me, it will probably take few weeks after this. And by the way, speaking about this thing, as I said, you can audit the course and this thing, and it finished, off you go. But for some of you who who want to get like I don't know whether it's useful or something, a piece of certificate or something, the requisite. As it stands, the requisite is that you do some work, ideally related to mathematics. Maybe you could submit something. It doesn't have to be like obviously it doesn't have to be Nobel Prize winning stuff. You know what I mean? And it could be, for those of you who are developers in the audience. I know there are quite few on the audience. It could be like contributing to an open source stuff. It has to have some mathematical elements. This is just to show us that the stuff that we cover here, very useful. You could use the knowledge that hopefully the little knowledge you gain here to do something. Okay. If it's the theorist, hopefully some of the stuff that you can submit, have some ideas. Okay. And you can do like a group submission or like individual submission. Okay. I'll once we get to the final of this thing, I'll share more on this. Yeah, I think a break would, that's what I was also thinking, because then you can digest, and those who want to submit something can submit, right? And it's also like, you can compare nodes like with the thing. It gives enough gap for you to think, because the next module, we will cover new things. You will know the algebraic side of things will be, easier, but then, you have the topological stuff. We will talk about like, we'll start with the topological spaces, for instance, and then we'll go through the concept of sigma algebras and all these things. So, these will all be like a new things for most of you, I would assume. But the good thing is the algebraic side will be a little bit more, easy for you, because you already did. Now, you will also hopefully find out that a lot of the stuff that happens in finite dimensional spaces do not generalize for infinite dimensional Hilbert spaces. Okay, the infinite dimensional Hilbert spaces are like a minefield, really. This is why it's so funny when I look, like sometimes I look at these talks, especially by physicists. Sorry, I'm not you see them with all these fancy integrals and these things that mathematically make no, like, say, what's this? If you are a mathematician. But yeah, anyway, I will keep you updated once we go through this the thing towards the end of this module, to see. Maybe I might even send a survey to say, how much gap you want before the next session start. I definitely, if it's me delivering the next module or parts of it, after this, I will probably do some traveling for a few months, because I've been in the UK on lockdown for almost 1 year. So yeah, that's it really. Is there any other comments, Soham, you want to add yourself or someone else made? Okay, George is saying, in the past, I must have learned about real vector spaces and matrices. Yeah. That's the thing with the most, like, if you are coming from engineering and these things, it's, as far as I know, a lot of the stuff, you normally work mostly with the real vector spaces, not complex, though they are complex vector spaces are finding their way more into industry, but mostly people are exposed because they are much easier to handle, though from a mathematical point of view, complex vector spaces are far more interesting. Yeah, in the context of quantum mechanics, actually, even for this finite dimensional cases Hilbert spaces that we'll deal with, you'll see also some interesting stuff. Like next week, we'll, when we talk about Hermitian matrices and these things, you will see some of the interesting properties that they have. The rest of their properties we'll cover on, once we go through the modeling aspects of quantum mechanics, to actually what Hermitians, how they are used in physics, to do, to say something about nature, a quantum system. Okay, so that's it really. So I don't have anything else to say, unless somebody have a final question, or Soham has anything else he wants to share. Maybe we can leave it here and we catch up next week, I guess. Apologies for the late ranting. This is what happens when the session is short. I can go on blah, 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 all this. Okay, so there's nothing. Okay, good. So everyone, it's, yeah, so please do chat. Someone is saying, please do get involved in the Gitter channel, and engage with each other. Okay, so yeah, I hope to see you guys next week. We are really getting into the actual interesting stuff that hopefully some of you, most of you, all of you on the audience, who have been very patient, this is where we are getting really into the cool, interesting stuff, really, that are really quantum related stuff. Okay, so I'll see you next week, and have a good weekend, everyone, and stay safe on the thing in these times of lockdown. And thank you to Soham again for helping. Okay, cool. Okay, so bye.